So far in this topic, I've talked about sprinting exercise. Now I'll go on to talk about endurance exercise and look at the fuel metabolism during endurance exercise and which pathways are the predominant pathways to produce ATP for endurance exercise. This is a repeat of the slide I showed a couple of videos ago of muscle from our fast twitch athlete, the high jumper, versus the marathon runner. And the marathon runner has all these slow twitch fibers, these lighter stained fibers, compared to the black ones, which are the fast twitch fibers, where the high jumper has quite a lot of those. And the characteristics of a marathoner, they have many mitochondria, they have lots of capillaries feeding the mitochondria with oxygen, and relies predominantly on aerobic glycolysis and the oxidation of fatty acids. So metabolically wise, the endurance athlete tends to rely on the metabolism that takes place within the mitochondria. So here's just some figures of what's required for a marathoner. So average VO2 for 2 hours, about 4 litres per minute, and these marathon runners are pretty small. Okay, so 4 litres might equate to around 70-75 mils per kilogram per minute. Okay, that's average VO2 for the whole 2 hours. Okay, not the VO2 max, but the submax VO2 that they can sustain for 2 hours. The energy equivalent of 1 litre of oxygen per minute is 21 kilojoules. So you should know that number quite well by now. So how much energy per minute? Around 84. So that's 4 times 21 is 84. So the total energy expenditure for a marathon is 84 kilojoules for around 130 minutes. So that's about 11,000 kilojoules, which is equivalent to the average energy expenditure for a male per day. Okay, but in this case they did it in 2 hours. So that's a pretty big turnover of energy. So here's some questions just for you to think about. Metabolic differences between a 100 meter sprint and the marathon running. What fuels are used during marathon running? What metabolic pathways are used during marathon running? Okay, so these are some of the things to think about as we go on to the next slides. The following table is a summary of research papers looking at the contribution of aerobic versus anaerobic. Okay, so starting up the top here, we've got the 5,000 meter event going down to the 100 meter event. So these are all running races that you will see in the Olympics. Okay, and they've calculated the aerobic contribution here, and this column here is the anaerobic contribution. So if we start at the top here, the 5,000 meters, almost 100%, 96, 97% aerobic, okay, which makes sense because that event lasts for about 12, 13 minutes for the best runners in the world. 3,000 meters, then slightly higher contribution of anaerobic capacity compared to aerobic. It's still very aerobic. Okay, 3,000 meters, a shorter event, around 8 minutes or so. Then 1,500 meters, so this is your typical middle distance type of run, looking at 3.5 minutes for the very best, okay, and still quite aerobic, around 80, 84, 85%, okay, if you get an average for those, and the rest is anaerobic. So there is a reasonably significant anaerobic contribution, around 15 to 20% for the 1,500 meter race. This is because 1,500 meters is run at above VO2 max, so at around 125% VO2 max, equivalent of VO2 max. Okay, so that requires a anaerobic contribution. 800 meters, it's about 1 minute 40 for the world record, 1:41, and still around 60%, 55 to 70% aerobic contribution and anaerobic contribution here. Okay, so we're starting to get closer to our 50-50%, which is more towards the 400 meters. Now the 400 meters starts to move more into the anaerobic range. Okay, so probably around 500-600 meters, if we had one there, would be around 50-50 in terms of aerobic anaerobic contribution. The 400 meters, while we're down, it's now predominantly anaerobic contribution, around 70%, 60-70%. Then 200 meters, primarily anaerobic contribution, about 85% or so. And then the 100 meters, getting close to 100% contribution, okay, for the 100 meters. So still some aerobic activity, but primarily anaerobic activity. So you can see how, in terms of the length of an event, the metabolic pathways become more or less prominent depending on the length of the event. So I've just done an average for all that previous chart, and this is the result. So 42 kilometers, that's your marathon. We're looking at 100% aerobic. Down to 100 meters, which is around 6%, 94% anaerobic. Now I've calculated what percent VO2 max these are run at. So the marathon's about 85% VO2 max for the best runners for 2 hours. So that's quite impressive. 10,000 meters, about 95%. And then the 5,000 meters is run at VO2 max. Okay. And then it increases. And then we get down to the 100 meters, and that's equivalent to around almost 1,700% of VO2 max equivalent. So imagine sustaining, if you could sustain that for longer than 10 seconds. Not possible. So in terms of energy expended, that's equivalent to, many times VO2 max, more than 10 times. And this is just a chart I plotted with distance and also aerobic, anaerobic capacity, and you can see the inverse relationship between the two. As the anaerobic capacity decreases with increasing event, then the aerobic capacity increases. The shorter the events, the higher the percent VO2 max, and then from 5,000 meters onwards, it's below VO2 max.